Hi everyone, this is Dr. Hira, and in this lecture, we will talk about and we will see how the solvents influence on the nucleophilic substitution reaction and what are the preferred solvent if we have to look into the reaction that is Sn1 or Sn2. So in the same lecture, we will also define some of the classification and the characteristics of the solvents. So let's start. The solvent is basically a component or the medium we are using for conducting a reaction. So this solvent plays a role of paramount importance in substitution reaction. The solvent importance is that much that it influences on the rates of both Sn1 and Sn2 reactions on relative nucleophilicity, because the selection of the solvent is so much important that either that can suppress or that can enhance the nucleophilicity of a nucleophile, and on the balance between Sn1 and Sn2 mechanism for secondary haloalkanes. Why? Because we have seen in from our previous discussions that secondary haloalkanes are those which are on the borderline, and they depend on the selection of the solvent along with some other factors, that either they are moving towards the Sn1 mechanism or they will opt the Sn2 mechanism. So you have seen in your laboratory that you do use the solvent for the providing the mobility of the reactants to mix together to have the good sufficient mixing and medium where this reaction is able to conduct with the high yield, with the good rate. And obviously, when we are conducting the reflux reaction or maybe the stirring reaction, some are the reactions which happen at the room temperature. So for some, we provide the heat and the reflux. So that solvent is very much important to keep your reaction in a balance. This is not, it avoid the chance to destroy your reagents if we are using heating up, because that solvent is providing that optimal temperature of the heating and the boiling one. So first we will talk about the classification of solvent. So common solvents are classified mainly as a protic solvent and aprotic solvents. So that is very important. So I would advise you that you should have the clear understanding about the solvents, because that information enable you to play with the reactions, to have a very nice planning for your reactions, that what could be the appropriate solvent for your certain reaction. So this information is helping you to be a good synthetic chemist as well. And one of that part, it will help you. So the solvents are mainly divided or classified as a protic solvents and aprotic solvents. And we will talk about in the next slide that how we can define aprotic and aprotic solvent. So both of these classification are further subclassified as a polar protic, non-polar protic, polar aprotic, and non-polar aprotic. And this polar and non-polar classification is based on its dielectric constant value. So this is basically the charge substitution or the separation, how much the value solvent as a molecule it contains. So then we will see that at what level or the range we will assign it as a polar, or at what range we will assign it as a non-polar. So firstly, we have to see about the dielectric constant, what it is. So dielectric constant is a measure of a solvent's ability to insulate opposite charges from one another. For example, if you have any of the molecule, and obviously if it is distributed because of some of the pull and the attraction, So there is a partial positive and partial negative charge. So what the solvent do is, solvent just come and host it, and it just engage that molecule, and it insulate it from again coming back to each other and retaining that original form in which it was in an original form. So that's why at a transition state, this solvation is very important one, because if the solvent is not able to cater these oppositely charged, so that is not separating that one. So you can just imagine if there is a fight. So the two parties, they are fighting, so they are the moderators who just take away both of these parties, so they are not have that much collision again, right? So but here this is in a positive side, that the molecule was happy with each other, but now we wanted to bring it into another form, into the product one. So that is important, that this charge separation has to happen, and to facilitate that charge separation, there is a role of the solvent. So as a guideline, a solvent is a polar solvent if it has a dielectric constant of 15 or greater. So if its dielectric constant value is 15 or above than 15, so that terms as a polar solvent. So that again is, we have to see that either that polar solvent is protic or aprotic. So if this is a aprotic by nature, by what functionality it has, so then it will be the aprotic polar or the protic polar, right? Now, a solvent where is a non-polar solvent if it has dielectric constant value less than 5. The solvents with a dielectric constant between 5 and 15 are the borderline. So they are the medium or the moderate solvents, we can say, in terms of the polar and the non-polar solvent term. Now we will see the protic solvent. So what the protic solvents are? A solvent that is a hydrogen bond donor. This is not the hydrogen donor. This is the hydrogen bond donor. So the most common protic solvent contain hydroxyl group, because then it is available and there can be the easily and hydrogen bonding can be formed. So this is the hydrogen bond donor. Common protic solvents are water, low molecular weight alcohols such as ethanol and methanol, and low molecular weight carboxylic acids. So here this is the table in which you can see the different solvents, and these all are the protic solvents because they are hydrogen bond donor, and which the hydrogen is directly bonded to uh, high electronegative element, right? And then it is able to form the hydrogen bonding. So there is a dielectric constant value, and if you just look into the table, so the highest dielectric constant from the formic acid, methanol, ethanol, and acetic acid as the water. So this is having the 79 So this is the polar protic solvent. Even the formic acid, methanol, and ethanol, they also come as the protic solvents, but the highest one is of the water one. So that's why we call the water as a universal solvent, because it can dissolve number of compounds or molecules. Even more of the organic range is um, good, can be solvated in the water as well. So in the latest studies, the people are still more interested to explore the organic reactions happening in the water, to moving towards a more greener side or the greener chemistry. So we are not using the hazardous or the toxic solvents. So water, formic acid, methanol, and ethanol are classified as polyprotic solvents, as I told you. And the acetic acid is basically the moderately polar protic solvent, because it's just around the 5 dielectric constant. It is having the 6 value. So this is just at the borderline, because otherwise less than the 5 is basically the non-polar protic solvents. And The 5 and between the 15 are termed as the moderate solvents. So they are moderately polar solvents. Now, the next is the aprotic solvent, a solvent that cannot serve as a hydrogen bond donor. So this is just opposite to the polar solvent. Nowhere in the molecule is there a hydrogen bonded to an atom of high electronegativity. So here you can see this is a list of some of the common. So this is not the complete list. These are basically the most common solvents which usually use in organic chemistry and synthetic chemistry and in our teaching labs. So you can see that the polar aprotic solvents are dimethyl sulfoxide. This is commonly known as DMSO. And there is acetonitrile, there is N-dimethyl formamide, DMF, and there is acetone. And if you just look at their dielectric constant value, so this is above 15, right? But one thing you have to notice is that this oxygen is not bonded to the hydrogen one. So there is no hydrogen in the molecule which is bonded to the high electronegativity element or atom. So this is not a hydrogen bond donor. Next is the moderately polar, and these are the dichloromethane. Then there is a tetrahydrofuran. This is a THF. So here you can see again the dielectric constant value, which is less than the 10, and this is now the non-polar. These are the diethyl ether, toluene, and N-hexane. So you can see their dielectric constant value is below 5. And you have seen when you are conducting the reactions, and obviously most of the students who have done some of the reactions and they have conducted the TLC. So when we are doing the TLC, we pick the non-polar solvent and we always go for firstly the N-hexane because this is a non-polar solvent. And if we are not sure about the TLC solvent, so we go for the N-hexane as a non-polar solvent, and then we mix it with another polar solvent to change the polarity, which is the most suitable and the best choice for a running or TLC card. For checking the qualitative analysis of checking the completion of the reaction. Now we will see the effect of solvent on Sn1 reaction. So for Sn1 reaction, the first thing we know is that there is the formation of carbocation formation. Then obviously if there is a carbocation formation, so we don't want that this leaving group is again coming back to that carbocation, and this is we are getting this reactant back in the reaction mixtures because we wanted to convert this haloalkane in one of the product that could be the ether, that could be the alcohol one. So that depends that what product we are interested in. Now, the third thing is that there should be the stabilization of the both positive and negative sides by solvation. So when the leaving group is leaving that molecule and there is a formation of the carbocation, so there is a need that we can separate these Cl negative and the C positive. So what will help us to doing that? So that is the rule of the solvent, that the solvent. So here I have just made that picture, the geometric picture of the water molecule. So there is an oxygen and there is a hydrogen. So technically there is the an error because hydrogen is smaller in size as compared to the oxygen one, but just for the showing because that shape was fitting fine. So that's why I have draw that in that way. So here you can see there is the, if any of the molecule is there, so there is the solvent which has a positive side, which has a negative side. So you can see that here you need is, so we can do one of the correction here because that should be the positive charge if we are referring this as a hydrogen. So though electrically this is just a univalent, there is a one positive charge, but this is just to show that this is the whole mass of this hydrogen, right? And this is the oxygen, and you can see that here this is basically the solvent system, and how this is engaging the Cl negative with the positive side of the solvent, and how this negative side will engage this carbocation, right? So here, this is the rate of the reaction of the Sn1, and you can see that there is the this has compared with ethanol, because in the ethanol, if that reaction was conducted in the ethanol, so this is the tertiary butyl chloride, and the rate of the reaction was 1. So then this chemists have worked on with the different mixture of the solvent to see that what is an impact of the um, more polar protic solvents, because we have seen that ethanol has the low dielectric constant value as compared to the water one. So then they use the 40% water, 60% ethanol, and the rate of reaction increased to 100, increasing the rate of solvolysis. So obviously that increasing the rate of reaction as well. Then there was 80% and 20, that was the 14,000 time, and then there was a water, and there was the 100,000 time. So that was the solvolysis, which has increased from 1 to 100,000 time in the presence of the water. So what we infer from this is the rate of an Sn1 reaction increase in higher polarity solvents, right? Now we'll move towards the next case, and that is Sn2 reaction. So effect of solvent on Sn2 reaction is somehow reversed to the Sn1. Why? Because in Sn1, we have the stable carbocation formation, and we need that there is some facilitation to form that carbocation, to retain that carbocation easily. And but in Sn2, what is happening, that there is a leaving group and there is a nucleophile. So the both things are happening at the same time. If you just look at this one, so this is a carbon and this is a leaving group, and because of the electronegativity difference, there is a partial positive charge and partial negative charge. So when the negatively charged nucleophile, which is rich in electron, this is approaching this one, so it means this is somehow giving that negativity, or the electron pull and towards that carbon to stabilize that one, right? It's positive charge, and there is the negative charge on this leaving group. So this is a transition state. So negative charge is dispersed in the transition state, because here is a nucleophile which is a negatively charged, there's a leaving group which is a negatively charged, and this is taking up that electron pair with that one. So this negative charge is dispersed in the transition state. Now, when it is converted into the product and the leaving group is completely leaving that molecule, so this negatively charged leaving group is there, and the nucleophile has just make a neutral thing, which the carbon to just stabilize its valency, right? So stronger the solvation of the nucleophile, the greater the energy required to remove the nucleophile from its solvation shell to reach the transition state, and hence lower the rate of the Sn2 reaction. I hope you picked that point, because if that nucleophile is solvated by the solvent, if we are using the polar protic solvent, so it will engage that nucleophile, because that is a nucleophile negatively charged. So what will happen, the nucleophile is already solvated and engaged by its so-called the fans. So this is not available for the haloalkane, which can only break its bond with the leaving group when it is able to see, oh, the nucleophile is here to help it, right? So if the nucleophile is facing difficulty to approach that one because it is too much engaged or surrounded by the solvent, so that will be harder for it. So that's why it will decrease the rate of the reaction in case of Sn2. Now, this will be more understandable for you in terms of their energy diagrams. So this is the SN1 reaction, and we have seen that one, that the reactant and the product energy difference was huge. And in SN1, there were multiple transition states, and there was the intermediate formation. So that is a carbocation formation, right? So what the solvent do is, so if you just look at this one, the activation energy, and there is the activation energy, right? If we use the lower polarity solvent, and this is with the high polarity solvent. So for when we use a high polarity solvent, what it do is that this carbocation is forming, and now this polar solvent is engaging that carbocation, and this carbocation is more stable. So it has a lower activation energy. So this is not facing any hardship to retain its stability in the reaction mixture. While when we use the low polarity solvent, so there is the difficulty for the carbocation to retain its stability, because there is no further facilitation. What it has to do, it has to do by its own self. So there is a higher activation energy. And remember, whenever there is a higher activation energy, it means this is the harder step for the reaction, and this is the hurdle to cross for the next step. So that's why in the lower polarity solvent, the SN1 reaction rate will decrease, while in the high polarity solvent, the reaction rate will increase, because the carbocation formation is more easy now in the presence of the high polar solvent. Now, if we just refer to the second figure, and that diagram is basically to show the SN2 reactions, and where we know there is only the one transition state and there is no stable intermediate. But when this reaction has happened in a higher polar solvent, and when it has happened in the lower polarity solvent, what has happened, because the nucleophile has to approach to the haloalkane, and the leaving group has to be moved. So if the nucleophile is facing the harder shape, so there is the higher activation energy, the more hurdle to approach to that carbon. So that's why there will be the decrease in the rate of reaction. So this is just a reverse and opposite to each other. And but you should keep in mind that why the polar solvents are facilitating the SN1 reaction, why the non-polar solvents are facilitating the SN2 reaction. So what we conclude from there? So our conclusion is, although the chemist may refer to use a polar aprotic solvent for an SN2 reaction, because it will be completed faster than when using a polar protic solvent. You should realize that SN2 mechanism viable in all solvent that dissolve the nucleophile and electrophile. Only polar protic solvents are viable for the SN1 mechanism. So SN2 somehow is more generous to accept the solvents, either the polar protic solvents and the non-polar protic solvents, right? But aprotic and the protic one, but the SN1 is basically having the limitation, because this is more viable, and it can happen to the polar protic solvent. So you have to be very conscious about SN1 reactions, that what is appropriate solvent you are using. So in SN2, this will happen, but obviously the rate will of reaction will affect, but it's not the case that this reaction is not happening completely. But in SN1, if you're not using the polar protic solvent, so that reaction is not going to happen um, as you consider a product and as a result. So that's for today, and we have covered the major factors, the experimental evidences, what affect SN1 and SN2 reactions. So maybe in future we'll talk about the stereochemistry as well. This is one of the challenging, a separate topic. So that's why I'm not including that in these discussions. Thank you. Have a good day.